Imagine this, a man standing in front of a roaring fire at 2 in the morning, sweat pouring down his face, hammer in hand, beating a glowing piece of metal over and over again. No electricity, no machines, no factory, just fire, iron, and a level of skill so precise that the weapon he's creating will still be sharper than a modern kitchen knife 1,000 years from now. That's not fiction. That's exactly what ancient swordsmiths did, and the science behind how they pulled it off is one of the most jaw-dropping stories in all of human history. Today we read going deep into every angle of how swords were made in ancient times. The materials, the fire, the folding, the secrets that were lost, and the mysteries that modern science still hasn't fully solved. Let's start at the very beginning with the material itself. The first real swords in human history weren't made of steel or even iron. They were cast from bronze, an alloy of copper and tin, and the earliest examples date back to around 3500 BCE in ancient Anatolia, which is modern-day Turkey. The process was relatively straightforward by ancient standards. Smiths would melt copper at roughly 1085 degrees Celsius, add tin to create the alloy, pour the molten mixture into clay or stone molds, let it cool, and then hammer and polish the finished casting into a working edge. Bronze was actually a remarkable material for its time. By adjusting the ratio of tin in the mix, a skilled smith could make different parts of the same blade harder or softer, depending on where that property was needed most. The cutting edge could be made harder. The spine could be made more flexible. This kind of intentional engineering, in 3500 BCE, is a reminder that ancient people were far from primitive. But bronze had one critical weakness. It was expensive. Tin in particular was rare, and the trade routes needed to supply it were long and fragile. When those trade routes collapsed around 1200 BCE, in the event historians call the Late Bronze Age collapse, entire civilizations fell apart, and the ancient world was forced to adapt. What emerged from that collapse was the Iron Age. Iron ore was everywhere. Unlike tin, it wasn't locked behind fragile supply chains. It existed in mountains, in riverbeds, in the ground beneath people's feet across Europe, Asia, and the Middle East. The problem was that iron was brutally difficult to work with. Bronze could be melted and poured into molds because its melting point was manageable. Iron melts at over 1,500 degrees Celsius, a temperature that ancient forges simply could not reach. So smiths couldn't cast iron. They had to invent an entirely different approach, and what they invented changed the world. That approach started in a furnace called a blacksmithing. Iron ore and charcoal were packed together inside a clay or stone furnace, and bellows, large leather pumps operated by hand or foot, were used to blast air into the fire. This raised temperatures high enough to reduce the iron ore into a usable form, but not high enough to melt it completely. What came out of the bloomery after hours of burning was liquid iron. It was a spongy, porous, red-hot lump called a bloom, shot through with impurities called slag. That bloom then went straight to the anvil. The smith reheated it until it glowed orange, then hammered it relentlessly, squeezing out the slag with every strike and beginning to shape the metal. This cycle, heat, hammer, repeat, could go on for hours, sometimes days. And here is where something extraordinary happened that early smiths didn't even fully understand. As that iron sat in the charcoal fire, carbon from the burning charcoal was slowly absorbing into the metal. And iron with carbon in it is not iron anymore. It's steel, harder, tougher, capable of holding an edge that pure iron simply cannot. The smiths didn't know the chemistry. They couldn't measure the carbon content, but they knew from watching, from feeling, from generations of trial and error, that metal treated a certain way and the forge behaved differently. And that empirical knowledge, passed from master to apprentice, was worth more than any textbook. The Roman Empire took this knowledge and scaled it into something extraordinary. Roman gladius, the short stabbing swords that conquered most of the known world, were made from blooms of steel that archaeometers, including research published in the journal Archaeometry, have confirmed contained carefully controlled carbon gradients. The Romans didn't just make swords, they standardized them. They built armories, trained dedicated bladesmiths, and supplied hundreds of thousands of soldiers with blades of consistent quality. Some Roman swords were constructed with a wrought iron core, softer and more flexible, surrounded by harder steel on the edge. The soft center prevented shattering. The hard edge held a killing point. This composite construction, achieved entirely by hand in a charcoal forge, reflects a practical understanding of materials engineering that would not be formally described by science for another 1,800 years. Now, if the Romans represented industrial-scale sword production, then the Japanese represented the absolute pinnacle of sword-making as a sacred art. The process of creating a traditional Japanese katana began not in a forge but in a riverbed specifically, in the collection of iron sand called satusu. This iron sand was loaded into a massive clay furnace called a tatara along with charcoal, and a team of craftsmen worked around the clock without stopping for 72 hours straight, feeding the tatara with precisely controlled amounts of iron, sand, and charcoal, managing the airflow through hand-operated bellows, reading the behavior of the fire and adjusting in real time. After 3 days and 3 nights, the tatara was broken open. What emerged was tamahagane jewel steel, a large bloom with varying carbon content throughout its mass. The master swordsmith would then take a hammer and break the bloom apart, examining each fragment, sorting pieces by carbon content with his bare eyes and hands. High carbon pieces, which were harder and more brittle, would become the cutting edge. Low carbon pieces, which were tougher and more flexible, would become the spine and core. These different steels were then forge welded together, the hard outer shell wrapped around the tough inner core, giving the finished blade its legendary dual nature, an edge capable of cutting through bone, mounted on a spine that would bend rather than snap under the shock of combat. Then came folding. The assembled billet was heated to around 900 degrees Celsius, hammered into a flat bar, scored down the center, and folded back on itself, then heated again, hammered flat again, folded again, folded again. This process was repeated anywhere from 12 to as many as 28 times. Each fold doubled the number of layers. 15 folds produced over 32,000 layers of steel. But no conversation about ancient sword making is complete without talking about the most mysterious blade in history, Damascus steel. Between roughly 300 CE and 1700 CE, swords made from a material called quenched steel, produced primarily in southern India and Sri Lanka, were traded through the Middle East and sold in the city of Damascus, which gave them their famous name. These blades were immediately recognizable by their surface pattern, a flowing, swirling, watery design of light and dark bands that looked almost alive, and their reputation was genuinely extraordinary. Contemporary accounts describe Damascus blades as sharp enough to split a silk handkerchief dropped across the edge, and flexible enough to bend dramatically without breaking. For centuries, European knights and Persian warriors alike sought them out, paying enormous prices for a blade that no European smith could replicate. The secret was in the raw material. Quenched steel was produced by sealing iron ore inside small clay crucibles along with organic matter-specific woods, leaves, and plant materials, and firing the sealed crucibles in charcoal furnaces for 1 to 2 days. The sealed environment and the organic additives created a steel with an exceptionally high carbon content of around 1.5% to 2%, which is what metallurgists today call ultra-high carbon steel. As this steel cooled slowly inside the sealed crucible, the carbon arranged itself into structures called carbide bands, and it was these bands, revealed on the surface during forging and acid etching, that created the legendary Damascus pattern. In 2006, researchers at the University of Dresden published findings in the journal Nature, confirming that historical Damascus steel samples contained carbon nanotubes, nanoscale, cylindrical structures that we think of as a product of 21st century nanotechnology, formed naturally through this ancient smelting process. The scientific community was stunned, and the bitter irony is that by around 1750, the production of authentic quenched Damascus steel had stopped entirely. The specific ortopazokes, the exact organic additives, the precise furnace conditions, all of it disappeared with the craftsmen who carried that knowledge. Modern metallurgists and blacksmiths have come close to recreating it, but no modern blade has yet been confirmed to fully replicate the microstructure of historical originals. Once any blade was shaped, whether Roman, Japanese, Celtic, or Persian, the work was still not finished. The most critical transformation was still ahead: hardening and tempering. Hardening began with heating the finished blade to a very specific temperature, identified not by a thermometer but by color. The smith was looking for a particular shade of orange-red glow that indicated the steel had reached its critical transformation point. For Japanese swords, the blade was first coated in a carefully applied layer of clay paste, thicker on the spine and sides, thinner on the cutting edge. This differential clay coating meant that when the blade was plunged into water, the thickly coated spine cooled slowly while the thinly coated edge cooled almost instantly. The result was a blade with the edge hardened into a razor-sharp crystalline steel structure called martensiite, while the spine remained tougher and more resilient. This quenching process also caused the two zones of steel to contract at different rates, which bent the blade into its famous graceful curve, a curve that emerged not from deliberate shaping, but as a natural consequence of the hardening process itself. After hardening came tempering, a second, gentler heating that relieved the extreme internal stress created by quenching, preventing the blade from becoming so brittle that it would shatter in combat. Ancient smiths performed this step by watching colors form on the polished blade's surface as it was gently reheated: pale yellow, then gold, then brown, then purple, then blue. Each color represented a different internal temperature, and the experienced smith knew exactly which color to stop at for a given type of blade. This knowledge, reading a blade by its color, took years to learn and could not be written down in any way that was useful. It lived in the eyes and hands of the craftsman. Finally, the blade went to the polisher. In Japan, sword polishing was an entirely separate profession, practiced by specialists who spent weeks working a finished blade. Through a graduated series of stones from coarse to medium to fine to ultrafine, each stone revealing more of the blade's true character, The final stages of Japanese sword polishing used stones of extraordinary fineness, eventually reaching a mirror-bright surface that allowed the hamon, the wavy hardening line running along the edge, to be seen in all its detail. A well-executed hamon is not just decorative. It's a record of exactly how the clay was applied and how the quench was performed. It's the signature of the swordsmith written in steel. What is so astonishing about all of this? The bloom forging, the tamahagen process, the Woots crucible. The differential hardening is that every single one of these techniques was developed without scientific instruments, without chemistry, without any formal understanding of metallurgy. It was all done by observation, by intuition, by the accumulation of error and correction across hundreds of years. The knowledge lived in the bodies of craftsmen, in their eyes that could read the color of fire, in their ears that could hear the right ring of the hammer, in their hands that knew the weight and resistance of the metal, and yet the results they achieved: carbon nanotubes, 65,000 layer differential hardening curves precise enough to make modern engineers pause. These are not the results of primitive guesswork. They are the results of a different kind of genius. A genius forged in fire, passed through generations, and built one hammer strike at a time.